Let's look at the other type of electrochemical cells, and those are electrolytic cells. In electrolytic cells, those are ones which consume electrical current in order to drive a non-spontaneous reaction. So we can consider, as an example of a spontaneous reaction, that would be hydrogen and oxygen forming water. So this is spontaneous. This reaction is used in fuel cells, actually. But if we supply an electric current, we can actually split water into hydrogen and oxygen. So this is actually one option for how to generate the hydrogen that would be used in fuel cells, because it can be difficult to have hydrogen. Sometimes this is done using a solar-powered electrolytic cell. We can look at an example of one of these electrolytic cells that's used in the splitting of water. So this figure comes from the book by Tro, and you see here at the anode that we have liquid water going to O2 gas and protons, and at the cathode we have the liquid water going to H2 gas and OH minus. This is driven by this external source, which in this picture is a battery, but that's where you could also have this be a solar-powered cell. So the power was generated from the solar cell, and that split the water and generated hydrogen gas and generated oxygen gas. You'll notice in this case, for the electrolytic cell, that the anode has still the oxidation reaction, but now it has the positive terminal, and the cathode has the negative terminal. Other examples of electrolysis, or of electrolytic cells rather, this can be used for plating metals, and we will look at how that works in just a second. This also could be used in order to produce pure metals. So many metals are not found in their pure state in the Earth's crust, but are found in some kind of oxide or salt. And so through electrolysis, you can generate the metal. An example of this would be sodium from sodium chloride. So let's consider how electroplating works. So in electroplating, the idea is to deposit metal on a substrate. So one reason you might want to do this is you might have sort of a cheaper but structural metal and then want to plate on gold or silver, for example, in order to make it look nicer. So we can look at a picture of how this works. So this figure also is from the textbook by Tro. And you can imagine, let's say here you have your object to be plated, so we have a ring. We hook up our power supply and we hook up our silver electrode if what we want to do is to plate the silver. So over here we have the anode, and silver is being oxidized, so the solid silver is going into the solution and the electrons are leaving. And then you see that's the plus side, and then over here is the negative side, so the electrons are coming down and the silver ions are recombining with the electrons to form solid silver on the surface. So that's how electroplating works. One thing we would want to do related to electroplating is to determine how long to run the operation in order to generate a certain thickness. So we can find the time needed to get a certain thickness. And to understand this, we are going to use Faraday's law. And Faraday's law tells us that there is a relationship between the charge and the amount of product formed. So accordingly, if we have 96,485 coulombs, this causes one equivalent of the reaction. So let's see what that means. This means that we either consume 1 mole of reactant or produce 1 mole of product in a 1 electron reaction. In order to solve these kinds of problems, we're going to need to keep in mind that 1 amp of current is equal to 1 coulomb per second. So if we know how long something is working and we know the current, then we can find the number of coulombs that have passed through. So let's consider an example that's for the electroplating of silver. So we have this reaction that silver plus an electron forms silver solid, and we want to know how much silver will be plated if the current is 5.5 amps and we run this for 25 minutes. So how much silver is plated? One thing that we need to know is the mass of silver, which is 107.9 grams per mole. So we know that the current was 5.5 amps, or 5.5 coulombs per second, and that ran for 25 minutes. And of course we have 60 seconds in a minute, and so we had a total charge of 8,250 coulombs. So now we can take that, and we are going to say that for 1 mole of electrons, we need 96,485 coulombs, and we are generating from this reaction 1 mole of silver for every 1 mole of electrons. This gives us in the end that we have 0.0855 mole of silver, and since we know the molar mass of silver to be 107.9 grams per mole, we find in the end that this will use 9.22 grams of silver. So if we run with a current of 5.5 amps for 25 minutes, this will plate a total of 9.2 grams.